Well, let's talk about some properties of functions. The things that we are interested in this section, the properties we're interested are even, odd, or neither, whether the function is increasing, decreasing, or constant, whether the function has any kind of maximum or minimum, whether it be it local or absolute. Now, the max and minimum are often referred to as the extrema of the function. And later on, I will explain what's the distinction between local versus absolute, which is also known as global extrema. So first, let's begin with even oddness of functions. Now, here I have a graph of some function for you. Notice the graph is supposed to be symmetric with respect to the y-axis. So when there is a symmetry with respect to the y-axis, if there is a point here on the graph, and I have this point as x, y, then the point in negative x and y, so this is the point x, y, and this is negative x, y, will also be on the graph of the function. So because of that, if we change x, the variable x, to negative x, we do f of negative x, and it ends up being the original function f of x, then that would be the indication the function is even. And remember, the implication of that is the symmetry with respect to the y-axis. If we change the input from x to negative x, and we get negative of the original function f of x, then the function is going to be odd. And here's what I have an example on this side of the screen. Notice if a point xy is on the graph, for it to be symmetric with respect to the origin, then negative x and negative y should be also on the graph of the function. Now, and then I'm going to look at some examples here. The first example is f of x equal 4x cubed. We want to know whether this function is odd, even, or neither. So I went ahead and replaced x with negative of x. So that means in the original function, you change x with negative of x. And I did, and once you do that, you're going to get negative 4x cubed here, right? The final work is negative 4x cubed. And that is negative of the original function, negative f of x. So this function is odd function. If we were to graph it, you would expect symmetry with respect to the origin. The next example is one that is neither, and that's f of x equal x plus absolute value of x. So how will this work? I've changed x to negative x, again in here, here, and in here as well. And then we just carry the algebra or the arithmetic in all cases. Negative of x, of course, is the same itself here. Negative absolute value of x, I've done the work here for you. We can write negative absolute value of x as absolute value of negative 1 times absolute value of x. And absolute value of any number is positive, so that's just absolute value of x. And that's how I got this portion. Now, this function that we have, f of negative x, is neither the original nor negative of the original. Negative of the original function should look like this. So notice right in here, that's where things are not the same. Therefore, we did not get the original function, and we did not get negative of the original function. Consequently, this function is neither odd nor even. Therefore, there is no symmetry with respect to the with respect to the y-axis or the origin. Now, there may be symmetry with respect to some other axis, with some other, with some other line, possibly, but it's just the y-axis that we are interested in this case. And remember, a function may not be symmetric with respect to the x-axis because it defies the definition of a function. If you have a relation that's symmetric with respect to the x-axis, that means you have a relation that fails the vertical line test. Okay, so we don't test for symmetry with respect to the x-axis, not for the functions. All right, and the last example I have is this one where g of x is 1 over x squared plus 8, changed x to negative x, and negative x squared in the denominator, of course, is the same as x squared. Therefore, I did get the original function, and again, the result, the function must be even. Now let's talk about increasing, decreasing functions. And this is the definition of an increasing function. A function is increasing on the graph. By the way, if you move your pen or pencil on the graph, as you go from left to right on the number line, you find yourself, or the pen or pencil or marker, rising on the paper. So in this case, something like this, the function is rising. Okay, so that would be the indication of a function that is increasing. Okay, and that's what that is. Now, algebraically, or we can make the statement that whenever x1 is less than x2, then f at x1 will be less than f at x2. That means, remember, x1, x2 are numbers on the number line. So that means that as you go from left to right, because x1 is below x2. So as I go from left to right, the function is greater at x2 than it was at x1 earlier. So that's, again, the sign of an increasing function. For the decreasing function, we have kind of opposite. As you go from left to right, that's what this is, x1 less than x2. As you go from left to right, then the function at x1 was greater than the function at x2, and means its initial point had a higher y value than the latter point. So that would be the indication the function is going down here. There you go, as I have it here. Okay, and there is your decreasing function. Let's take a look at the constant function. A constant function is just that. It's one that does not change, so it's flatlining. And whenever you have two different points, doesn't have to be less than, greater than, doesn't matter. As long as you have two different points, you get the same function values. And again, that would be the signature of a constant function. And here I have made an example of a function. There you go. So I tried to make it as symmetric as I could. Therefore, because of the intended symmetry I had in mind, we're going to say this function is even. Now, I don't have an algebraic formula for this per se. I just drew something that visually is symmetric. So I know this function is even. Now, what is the domain? Let's go through some of the characteristics of the function. So the domain of this function is going to be from -4 to 4. Remember, for domain, we look at the x values. And there you go. There's the domain. And I have written the domain in both interval and set builder notation. What about the range? Well, the range is possible y values, right? And y values here are along the y-axis. And if you look at, for example, this point projects onto the y-axis, this point projects, all points project into scale that runs from 0 to the highest point, max possible is 3. So the range means all possible y values here are going to be 3. All right. Now, for increasing or decreasing, if I go from left to right, and remember on the number line we always go left to right. So as I go from left to right, I can see that this portion of the graph, notice how it's decreasing. And it's also decreasing from 0 to 2. If you look at again the function, it's going down. So it's decreasing. For increasing, if you go from -2 to 0 on the x-axis, the function is rising. So it's increasing. It is also increasing as you go move from 2 to 4. So right in here again, the function is increasing. And again, in this book, your author uses brackets to include the points that are decreasing or decreasing. In other words, the end of the intervals are included. However, at -2, if you look at -2, that's the transition point. How can it be both increasing and decreasing? So some authors, some textbooks actually use parentheses for the endpoints, but again, this author does not, and I'm going to go with this author because that's the book we're using. Okay, and that pretty much settles the idea of increasing and decreasing. Now let's talk about local and absolute extrema, or max and minimum of a function. So let's first begin by local. I'm going to call them extrema. Your book does not call them extrema, but they will call it that in calculus and higher. Okay, so I'm looking at local extrema here. So what do we mean by local extrema? Well, I'm going to let C, okay, be a number in an open interval. An open interval in some interval I. So notice I have kind of like an interval within an interval. I have an open interval in I inside of an interval. Okay. Now, if f at c is greater than or equal to f of x, the general function, for all x in the open interval, then we have what we call a local maximum of the function. Okay, local max of f. In other words, when we say f of c is greater than or equal to f of x, that means there is no point higher. There is no point higher than f at c. So that would be the definition of a local maximum. What does this look like on a graph? Let's say here I have an open interval that runs from, say, a to one of the maximums. Sorry. There you go. A to C, A to B, and then this would be C right here. So my open interval again runs from A to B. C is somewhere in there, and if you look at this point, is the highest point on the graph. So the highest point is going to be f at C. Other points, all these other points, are just f of x for different values in that interval from A to B. Okay, and don't worry, I'll bring it back on there. So that's the definition of a local max, L max for short. Okay, now if f at C is less than or equal to f of x, and that would be again for all x in the open interval. Again, this time it means there's no point lower than that. Previously it was higher, this time is lower. In an open interval, therefore, we have what we call a local minimum of function f. So to do a graph of this one, suppose I have, there you go. Here's my coordinate system, let's say xy, and we're looking for local minimum. And this is my interval that runs from A to B, open interval from A to B. And this time C is the lowest point right in here. That's going to be f at C. This time f at C is a local minimum. Okay. Now, and then we have, so this was local extrema, and then we have absolute extrema. The difference between local and absolute is, for absolute, or also we call it a global extrema. For absolute, we look at the entire domain, not an open interval inside an interval, but we look at the entire domain of the function. So suppose this time, I'm going to say let f be defined on some interval I. Okay, so suppose we have a function that is defined on some interval I, and this time instead of like f at C, we're going to say if some number u inside of that interval I, okay, for which f at u is greater than or equal to f of x for all x. And x has to be inside of that interval. By the way, this is the membership, means inside the interval. Okay, the symbol looks like this. It's the set membership, means x belongs to the interval. Okay, that's what that symbol is. For x inside of that interval, so I have if u is in an interval for which f of u is for all x inside of that interval. Okay, then we have what we call an absolute maximum. So we have an absolute max of the function f on I. Okay, now the other way to look at this for the minimum this time, instead of u, I'm going to go v. Suppose v now is inside of an interval for which, and this time f at v is going to be lower than or less than or equal to any other f of x over the entire domain. This time for all x in I, not in an open interval, but over an entire domain. I here is the domain of the function. And then in this case, f at v is the absolute or global minimum of function f on I. Okay, so now to give you an example of this one, let's say I'm just going to quickly create a function. All right, and this function is going to look something like this. Okay, now the arrows mean this extends indefinitely, right? So if I'm looking for absolute max, this one is none. See that? Because the function grows indefinitely. On the other side, if the arrow is there, then there is no absolute minimum. No absolute minimum. However, there's a whole bunch of local extremas, right? So for example, if I look at this interval, right there, I have a local min. Let's see, sorry about that. Let's see if I can, there you go, it was something like this. So I had a local min, and my local max just moved. Sorry about this, not sure what's happening here. Okay, I corrected it. Sorry about that. So there's still no local, no absolute minimum, no absolute maximum. But there's local min, so in this interval there is a local min here. In this interval there is a local min here, correct? Looks like there is a local max here in that interval, and there's like a local min here, there's a local max here, and so on. So you see these local extrema occur in an open interval within the domain of the function, the larger domain, which goes from negative infinity to infinity on this one. Now, one thing to note here, for example, is that sometimes the local max and minimum, the local minimum in one location is going to be actually bigger than the local max elsewhere. So for instance, there you go. Suppose I have a function that looks like this. This time I have a closed interval, right? So if I have a closed interval, suppose that is the domain, that is the I, the interval. So at this point now I have a local minimum, I'm sorry, this would be an absolute minimum, and this point looks like the highest point on the graph. That would be the L max, correct? And let's see, so this is what I was going to say. Notice this is a local minimum, right, in that interval, and here's a local max in that interval I have. So the local minimum in some part is actually greater than the local max elsewhere. So these local minimum and maximum, the local extremas, again, it could be whatever. We cannot compare them to each other, right? So that's just what I wanted to point out, that the local max for some interval could be actually lower than local minimum somewhere else, and vice versa. All right, so that will pretty much wrap up what we wanted to talk about in this section. So we did talk about, in general, some properties of functions, even, odd, neither, increasing, decreasing, constant, and we just finished up with discussion on local extrema of the function. Okay, so with that, we are done with this lecture. Thank you.